Ankush. I'm an applied scientist at AWS, and I'm going to be talking about how you can gain confidence in your system's correctness using formal and semi-formal methods. So I'm the first one to talk about formal methods here, and I know as soon as I say formal methods, there is a lot of skepticism in the room. I'm from the same, I basically work in testing, and I really think that formal methods is a way in which you can really push the limits in some ways for testing. Past 2 days, we've been talking about testing. And there is a consensus in that sense that testing is hard, right? Especially doing end-to-end system testing, scalable testing, and so on. But even if you do simple testing, it adds value, right? So the same thing can be said about formal methods. Formal methods is harder, maybe like way harder than testing. But if you use simple ideas from formal methods, they can still help you in making your system more reliable. So, and that is the key lesson I want maybe all of us to take from this talk. Okay? So there's going to be no math, there's not going to be anything hard here. It's all going to be very simple things that you can use from, concepts that you can use from formal methods to make testing and reliability of your systems better. Okay? So why are we here? We all agree that programming distributed systems is challenging, right? It's like putting together a complex piece of puzzle where all these pieces of puzzle need to fit together. For example, when you're trying to build a distributed system, you would want your distributed system to satisfy these core demanding requirements like availability, scalability, correctness properties like consistency. You want your system or a storage system that you're trying to build to be strongly consistent or eventually consistent and so on, right? And you want your distributed system to satisfy these properties in the presence of all the non-determinism that exists in a distributed system. Network failure, concurrency, node partitioning, network partitioning, message loss, arbitrary failure of nodes, and so on. And obviously, when you're trying to build a distributed system that needs to satisfy all these properties in the presence of all the non-determinism, it can never be a monolithic system. It got to be a compositional system, which consists of all these multiple components, multiple protocols at different layers coming together such that your system satisfies these properties. And which is what makes reasoning about distributed systems hard, right? And for the same reason, we have all these guardrails in our development process to make sure that if there exists a bug in our design, we can catch them as early as possible before they reach production. Okay? And I'm completely on board. All these guardrails are important. They are there for a reason. Okay? But the key goal here, as we all know, finding a bug in production is way costly in so many ways. And we would like to eliminate these hard bugs, especially design-level bugs, which fixing them is super hard and needs changes in several layers of your protocol stack to be found as early and as soon as possible in your process. So shift left, right? And with all the automation and innovation that is happening around, especially like maybe antithesis and so on, these guardrails are going to stick, okay? And I want to reiterate, we do work on testing. I value testing, I value observability, and all these things super, they are there for a reason. And we recently wrote this article about different practices that are being currently used at AWS to reason about system correctness. And all the things that we talked about over the past 2 days are mentioned there. We use them all the time. They are important for eliminating bugs. For example, recently Amazon launched DSQL, which is the distributed SQL. And when building the distributed database, we used differential testing. We used deterministic simulation. We used property-based testing. We continuously do SQL fuzzing to find correctness bugs in SQL semantics that can be there in the database. So all these things are there. All these things are important. But the key thing is, what more can we do, right? Like, what more can we do to find critical bugs early so that we reduce the pain later on? And formal methods can play an important role there. The reason why I say that is, one of the key understanding or the key lessons that I have had over the past few years is there is no replacement for thinking. Okay? In some ways, you need to force the developers to think hard, what are they building? You can't skip this part. You can do as much testing as you want. You can do as much observability as you want. But if you ask your developers to move fast and not spend the time required for testing or thinking, it's not the right recipe. Okay, that's the key lesson that I learned. And one of the ways of enabling thinking and forcing them to write specifications may not be mathematical formulas. Please, whenever I say specification, there is this tendency of connecting specifications with math. Don't do that. Spec could be programs, okay? But spec and thinking are the key part that are important and cannot be replaced, okay? And more importantly, Gen AI is coming in, right? But then still, if you want Gen AI or any of these LLMs and so on to generate code for you automatically or generate test cases for you automatically, it still needs to know what are you building, right? And we need to tell them what the system is supposed to do and what are the guarantees that the system must satisfy. And then maybe hope that Gen AI will be able to figure out the coding part and the testing part, but then still, there is no replacement for thinking, okay? And specifications. When I say formal methods, I know that we might have all heard about formal methods in different ways. Like some of them might think of formal methods as a pen and paper proof because you're coming up with a new protocol design for the very first time and you just want to do a pen and paper proof for it. It could be that you're a hardcore formal methods person and you want to do a formal verification of your system with an end-to-end correctness of your system. It could be model checking using TLA plus or P or any of these techniques. Or it could be as simple as doing property-based testing of your system, right? Because in the end, for doing property-based testing, you need to write the property, right? Which means you need to know what are the correctness properties of your system. So a very general definition that I would like to put out as the definition of formal methods that might stick with all of you is you can think of formal methods as any process that involves writing specification of your system and checking that your system's behavior satisfies those specifications, okay? Again, specifications may not be mathematical formulas. It could be programs that at a higher level of abstraction tells you what your system is supposed to do, okay? But the key thing, which I again would like to stress and is the important part, is going through that process of writing specifications for your system. That's a very, very important part. And hopefully by the end of this talk, I'll be able to send that message out that, hey, the process is the key here, okay? And obviously, I'm not the first one to talk about this, right? Like scientists, researchers, people who came up with the concept of distributed systems have been talking about this for ages now. Like the part about the importance of thinking about your system abstractly, the part about just thinking about your system at a different level of abstraction before you move on to implementation. And these things have been around for a while. But what do we mean by that, right? So what does it even mean to think about a distributed system or a system that you're trying to build at an abstract level? So let's say we are trying to build a distributed system for the very first time, okay? What are the steps that you would go through? The first step itself is to basically not dive into the implementation right away, but take a step back. Okay? Take a step back, think about what is the system you're trying to build, what are the components in my system, how do these components interact with each other, what are the messages that are being exchanged between this system. More importantly, like what is the assumption that is being made by a particular component about the other component when it's interacting with them, right? And above all of this, what is that particular customer-facing correctness specification that I want my system to always satisfy in the presence of all possible failures and interleaving of messages, okay? And once you have that clear understanding in your mind, then you can move on to the implementation part, right? But obviously, thinking is not enough. The next thing is, and the key part, is thinking at the right level of abstraction. At a level of abstraction where you basically can ignore all the internal details about your system, which are not important from the point of view of correctness, but are there for performance and other reasons. So for example, most of the times when I'm interacting with service teams who are trying to build an important thing, one of the very common exercise that I conduct is I ask questions like, hey, what happens if I comment out this piece of code in your pseudocode or the system design? And then, is it there from the point of view of performance, or is it there because it will break a particular invariant in your system or a correctness property in your system? And gaining that level of understanding at a higher level of system design is very important, so that you know what are the pieces of the code or the design in your system that cannot go wrong. And the others are there for performance reasons. And all this requires thinking about your system at the right level of abstraction. What are the components that are in the critical part, what are the components that are not, and so on. And once you have that, then comes the part about writing this thinking down in certain ways so that you can test and reason about that thinking in itself. And finally, when you're building a real service that is used by customers and so on, a design is not static. It's never static, right? Design evolves as the customer demand changes and so on. So you're going to go through these iterations where you came up with the first design, you deployed the system, now you want to make it more efficient. But when you're making it more efficient and you're doing an optimization, you want to make sure that the optimization is deployed without breaking any correctness properties. Right? So there's this iteration. You need to go back to the design. You need to reiterate over the design and make sure that the changes that you're making is not breaking anything in your system. So what would be super cool is if you have a tool that allows you to iterate over the design and get a design that the whole team is confident about, that it's correct, it satisfies the desired correctness specifications in the presence of the failures and so on. And which is where we've been using P, which is like a high-level state machine-based programming language that allows you to model your system design as communicating state machines. So, which is how normally system designer or developers think about their system as a set of processes or a set of state machines that talk to each other by exchanging messages. And once you capture your design in this high-level programming language, P has this back-end analysis engine. You can think of it as a scalable or glorified testing engine, where at this higher level of abstraction, then it tries to interleave all possible messages in your system, all possible failures in your system at the design level, and make sure that your system design then satisfies the desired correctness properties, which are specified in P as state machines. Okay? So, and once the P checker has done that, obvious question would be, hey, design is not what gets shipped, right? It's the implementation. I can spend n number of cycles trying to get my design right, but it's the code that gets shipped. How do I make sure that my design and my code satisfy the same correctness specifications, right? So we have a way in which we allow connection between the design level correctness specifications that you showed to be correct, and then connect them to the implementation. And that is what closes the loop for the service teams. So you can think of P as a way in which you can enable the design iterations that I talked about in the previous slide. Okay. So P is being used inside AWS by service teams across compute, storage, databases, and so on to reason about the correctness of their protocol design and system design. And so each time they are trying to come up with a new protocol design, they would try and in the design review, create the P models of their system, reason about its correctness, and then gain confidence that the design is correct, and then move on to the implementation. And the P got its first start basically when Amazon S3 was trying to go from being an eventually consistent system to a strongly consistent system. And the service team, when guaranteeing strong consistency, were going to make several changes in their protocol stack across the layers, and they wanted to make sure that these changes actually satisfy strong consistency. And they were not able to basically make sure that the design is correct, which is where the service teams created formal models of their distributed system in P. How do this caching layer, routing layer, the storage layer, and so on interact with each other as P state machines? They wrote down the correctness specifications for their system. In this case, it is a strong consistency in P, and then use the backend P checker to explore all possible interleavings of the system systematically. And as you could very well imagine, as now you're trying to reason about your system at this high level of abstraction, and the probability of uncovering a corner case scenario that could lead to a violation of strong consistency is way higher than trying to use traditional traditional testing approaches to uncover the same bug. So the team was able to eliminate several design level bugs in their system using P and uncover cases which basically they were not able to uncover using testing approaches. And this gave them a lot of confidence in their system design. And from that point on, now service teams across AWS, before moving on to implementation, or if they have a idea that they're not very confident about, for even going for a review with their PE in the team, they would first go and create the model, gain understanding, try it out with different inputs and failure scenarios, and then move on to the review and implementation process. And one obvious thing that you might be thinking is that, hey, like, what is there a magic inside the P checker or something? But to be honest, there is not. Like, it's a very simple idea, which maybe Antithesis also uses, or any other systematic testing approaches tend to use, right? So you can think of what P checker or model checkers are doing. Basically, it's a search problem over the state space of the system. So you have a system, you have a composition of collection of processes, and you want to explore at any point there are n number of interleavings that can happen in the system, or n number of messages that can be explored at that particular state. What the backend checker is basically doing is trying to explore all possible interleavings or combinations of them. Okay? So at a particular point, you have message A, B, or a failure that can happen. What the checker is doing is basically it interleaves all of them systematically. And for each of the state that are reachable in your state space, it asserts that it satisfies the required global invariants that you want your system to satisfy. Okay? Obviously, many of you have built complex systems, and you would have been like, oh man, the kind of system that I'm trying to build is so complicated that this kind of systematic exploration is not going to scale. The state space is just exponentially large. So, and that's where basically formal methods or mathematics comes in, where you try to scale this kind of search techniques to larger state spaces. But in the end, even if you're not able to explore all possible states in your system, just doing this at a higher level of abstraction and then doing this exploration drastically improves the probability of uncovering a corner case scenario that is super hard or has a very, very low probability of happening on a production or a pre-production integration test environments, right? So that's where the real value is. The value is not really like math or the efficient search algorithms and so on. The value is doing analysis at a higher level of abstraction, where you have removed all the unwanted things from the point of view of correctness, and then just using simple ideas like interleavings and so on to find corner case scenarios. It's a probability game in the end, right? You are increasing the probability of uncovering a corner case scenario if you're reasoning about it at a higher level of abstraction. That's as simple as it is what is happening here, okay? So outside of AWS, we recently have a nice use case. Microsoft and others have been using it as well, but recently DeepSeek released their file system that they use for inference and so on. And when they open source the file system, they also open source the full P models for their file system. They use chain replication. They open source the full P model. It's around 10,000 lines of P code that clearly describes how the protocol works and with the correctness specification. So it's very cool. I or nobody in the team was involved in this. So it's an anecdotal data point that P is easy to use. And the cool thing I wanted to highlight here is something that I've been iterating over, and I hope that this sticks, is that the team basically used P to gain clarity in their design. So each time, basically, they created, it acts as a pseudocode for them, as a reference implementation for their actual implementation. And each time they were making some changes, they would go and change in the reference implementation, because it's a smaller piece of thing that you can reason about, you can fit into your head and do things. So having P models is important, and when you're trying to build a complicated system, because you can iterate, find bugs, eliminate issues. Once you have gained confidence that your system design is correct, you just need to mimic it in your implementation. I know it's not a simple thing, but I'm just making it sound simple. I knew there would be a reaction, but you get what I'm trying to say. Okay? I know there is a huge gap between the two, but the gap becomes even bigger if you don't have that intermediate mode of creating a system design. The gap then would be something that you thought in your mind and implementation. So I'm just trying to reduce the gap. There's still gap, right? So what do we do right now is we have integrated formal methods in our development process. Is where instead of design code implementation, you first do some reasoning about it using P and then move on to implementation. Okay. So coming to the part about design, like I talked about design a lot, right? And I know that the reason why we do testing is because it is actually working on the artifact that gets shipped. Design is not what gets shipped, right? So we obviously have a connection between what gets deployed and the implementation through observability, right? Which many of the speakers have talked about. So there is this natural closed loop here between what you operate and what you implement. But the gap starts to become more and more between what you design and what you implement, right? And how can you close that loop? Okay, it's very important to close that loop. If there is a way I could, that make sure that there is a point once you're trying to change what you operate to go back to the design. Many a times what we have observed is that design happens, system gets deployed. Now you want to evolve the system because there are new feature requests. People jump into implementation. So they don't go back to the design. And the reason could be that the implementation and the design has moved so far away, there is no point in going back to the design, right? So the way we solve this problem is we've been working on this thing called P-Observe, which is a way of continuously monitoring global invariants on your system implementation. And when I say system implementation, basically service logs, right? And these service logs could be from anything. It could be from testing, it could be from pre-prod, it could be logs generated in your production. And we continuously monitor the specifications written in P, converting them into runtime monitors, and we monitor them on these service logs continuously. So that's what now creates a connection, and basically the way I would like to throw it out for the observability folks, and the way I think about it is that it's improving the observability of distributed system through the lens of formal specifications, okay? Because normally for everyone, like observability is metrics and logs. Now it could be formal specifications, okay? So that's where P-Observe is now trying to bridge that thing and create a connection from the design to operation. And the cool part now is that if you change, and if you're changing something in your system that is deployed, which changes the specification of your system, there is now a way and a push to go back to your design, make that change, improve your specifications about the system, and then updated specifications is what gets checked across your development process. Okay, so now there's a closed loop. In doing all of this, the thing that I'm repeating again and again is formal specification. Like that's what everybody now agrees on. And for example, for S3, everybody agrees that I have to be strongly consistent, and I cannot violate that specification in any phase of my development process, be it testing or and so on. So I'm going to kind of like, I left 10 minutes in the end, so it's going to finish pretty soon. But so that we can have questions, or we can take a break. But I wanted to like talk about what are the key lessons. So when and this is in formal forum anyways, right? So I did my PhD in formal methods. So since I have 20 minutes, I can go. Right, I can do a detour, right? So when I graduated, I did my PhD in formal methods, and I was one of the most pessimistic person that, hey, this thing just won't stick in industry, right? But then the S3 team was trying to build strong consistency, and there was someone who felt like, hey, okay, I think you can come in and see if this thing works or not. And initially I was again pessimistic because of all the reasons as you all are, right? But then when trying to apply this over the next 6 years, I find that there are few things that are important, and maybe we can explore these ideas further. And these are the things that actually add value through formal methods. And when I say formal methods, again, the general definition of it, right? The first lesson, which kind of like is what I try to convey normally, is that it's acting as a thinking tool, okay? Which is if any one of you have used P, or when you try and use P, there are some steps that you go through. And the first step that you go through when you're trying to use P is you need to populate this folder called P source folder, which is, you can think of it as, you populate this folder with formal models or mocks or reference implementation of your system. These are these state machines and the detailed design of how these components interact with each other. And when I ask service teams to do this, it forces them to think about, hey, what are the core components that I need to think about when I'm reasoning about the system? What are these events that are being exchanged between these components? And so that gives them a kind of understanding which they normally don't have as to what is it that my system is supposed to do. Okay. The next folder that you normally populate, I ask them to populate, is okay, now you know what you're building. But do you know why you're building this, and what are the core properties that you want your system to satisfy? And that's why it's being built like this. So you have to populate this formal specification folder, which are these global invariants that needs to hold always for your system. This could be customer-facing global invariant. For example, for storage systems, this is consistency. If you're building a control plane protocol, because there is a single writer system in it, then the global invariant could be there is always a unique leader per partition, and so on. So these are the invariants that cannot go wrong in my system. Okay, and also, like, apart from the customer level or system level global invariant, you also need to write component level global invariants. So for example, in the storage system, normally when you're building a distributed system, there are these component level invariants that needs to hold, that the storage system always accepts monotonically increasing writes. And so on. It never accepts writes that are out of order, and so on, right? The whole global invariant holds because component level invariants hold. So now when populating formal specifications, it forces the corresponding sub-service teams to agree that these are the component level specifications based on which the system is in the end going to work correctly. Okay, so again, it kind of like forces them to think about and again, formal specifications, it could be, even if it's not mathematical formulas, it could be written as English text. Even that is hard, right? Like, and finally, populating the p-test folder. So when you're trying to build a real service or a distributed system, it's an open-ended system, but it's never going to work under arbitrary failures or arbitrary input scenarios, right? So what are these inputs, or what are these failures under which my system will always satisfy the correctness specifications? And so for example, Paxos is always correct up until minority of the nodes are down, and so on, right? So those kind of constraints, like so what are the inputs under which, what are the input interleavings under which my system is supposed to be correct? What are the workloads under which my system is going to be available, and so on? So going through these iterations as the service teams are getting their design right forces them to think hard. And now once you have this, you have everything documented, right? One of the key lessons that I have learned is that thinking formally works magic. Okay? What I mean by that is, if you force developers to go beyond their coding and like take a step back and do some kind of thinking in a different way, they are super smart, right? Like, I'm a developer, I'm smart. No. But all the developers who build these services, they are super smart. They can extrapolate as they are thinking as to what are the gaps in my design and how I was thinking. So just giving them a way in which they can think works magic. And in my experience, a majority of the bugs in design were uncovered in the thinking step itself without even running the checker. Okay? And that's the key lesson I wanted to share, was that it doesn't matter whether you use mathematical proof, whether you use a systematic testing, whether you use antithesis or whatever it is. Even before hitting that point, if you just spend some cycles thinking rigorously, a large fraction of the gaps are uncovered in that step itself, which is where the hope is. And obviously, thinking cannot uncover all the bugs, so you need something like a systematic explorer to find these bugs for you. And the key thing here is to take control of all the non-determinism in the system and then systematically explore it. And doing this kind of systematic exploration at a higher level of abstraction is super valuable. So again, this is not P-specific. If you're using some other tool, you can very quickly come up with a way in which you can build a random simulator for your system, and then doing this kind of a fast analysis is going to uncover a lot of bugs for you instead of trying to uncover them in production or in testing. Okay? And yeah, I think I already mentioned this, so it's fine. And the final lesson that I wanted to share was that, which is now that we've been doing this for a while, is formal methods and this kind of rigorous thinking takes time to show effect. Okay? And the key thing that happens is that once you have a reference design in place, you can now do faster iterations on your system. Many a times I have seen where service teams are reluctant in doing certain optimizations because it will break the system. But now, since you have a reference design in your case, you can try out this optimization, run the p-checker at scale, gain confidence that these risky optimizations are not going to violate any design level property violation. And once you gain that confidence, then you try and go down the implementation. So the amount of time teams spent in reviewing and thinking about risky optimizations have gone down a lot. And that overall boosts the velocity of developers and the way they can gain confidence in your design once you put this into your development process. So it ends up boosting the overall velocity of the team itself, because now they can do rapid iterations over their system. So finally, I would like to see a world where we don't have to make a choice. Like I said, I'm pro testing. Like, if you go and read my PhD thesis, half of it is on testing. But I don't think we need to make this choice of, hey, whether I should do a testing or formal methods. Both of them, I should be able to have both the pills, and I would love to. So I think there is a place for both of them. They have their own value. So yeah, I think that's the key message. And yeah, those are the key takeaways. I won't iterate because I may be repeating a number of times now, but that's all. Yeah. Thanks a lot, everyone. Thanks for it. And